Hi students. So yesterday we talked about second order differential equations. Particularly we looked at second order linear differential equations. Now if these differential equations, the second order linear differential equations have constant coefficients, that means the coefficient of the y prime term is a constant term like 1, 2 or 3, or the coefficient of the y term is a constant. Then we call it as with the constant coefficients. These equations are quite special because they are even simpler, and which we can convert these differential equations into a form of an algebraic equation. We know that solving an algebraic equation is much easier than solving a differential equation. So what we do is we solve this algebraic equation and then use those solutions to write down the solution of the corresponding differential equation. Okay, so that's the idea, and this idea can be extended into higher order linear differential equations with constant coefficients. We will look into those again perhaps in the next lecture when the differential equation is higher order. Okay, today we will look into higher order differential equations in general. Okay, so let's say I have an nth order differential equation, which means in that differential equation the highest derivative term is the nth derivative. If, for example, if it's a third order differential equation, then we have a third order derivative term in that equation. That's the highest. Okay, so now how can we find out the solution in general of such higher order differential equations? Again, as we talked yesterday, we can decompose these differential equations into two categories: homogeneous equations where the right hand side function is 0, and non-homogeneous equations where we have a function in terms of our independent variable. Okay, so I told you that's much easier and straightforward to solve the homogeneous equation. So we'll learn about how to solve the homogeneous one, and then later we will also going to learn about how to solve this non-homogeneous equation. So let's call this homogeneous equation have a solution which we called as the complementary solution, and the non-homogeneous equation, if we can find a particular solution that satisfies this non-homogeneous solution, the non-homogeneous equation, we will be able to find out the general solution of the entire equation by combining the complementary solution, which is the solution of the homogeneous equation, together with that particular solution that we found. So that is a result of a theorem. We're going to learn a bit more about this theorem and how it works. And again, if we look at what a homogeneous nth order linear differential equation, if we can find n linearly independent solutions to that homogeneous equation, we will be able to find out its general solution by looking at a linear combination. It's very similar to what we did for a second order linear differential equation. That's what we're going to sort of like discuss during this lecture, and I hope you will enjoy it. See you.